So today we're going to talk about how to approximate a binomial distribution using a normal distribution. So we can use the normal distribution to approximate a binomial distribution whenever it would be impractical for us to use the binomial distribution to find such a probability. So we're going to use the same setup that we had before. So n is still going to represent our number of independent trials. P is the probability of success in a single trial. Q is the probability of failure in a single trial. So why would we want to do this? So let's say, for example, we had a binomial experiment where n was 850 and you wanted to find the probability that, and in this case I'm going to use R for binomial, so the probability that R is greater than or equal to 600, whatever this is defined as success for. Well, if you think back to how we would have had to have done this in chapter 5, then we would have had to either add up the probability that R is equal to 600, 601, 602, 603, all the way up to 800, or 0 all the way up to 599. Assuming that there was even a table for this many values of trials. But instead, this would be a good candidate to use a normal distribution if we can approximate it by a normal distribution. So let's talk about when we can actually do this. So I mentioned where it being practical to use the binomial distribution, but there are still some conditions that apply before you can actually do a binomial approximation with the normal distribution. So what has to happen? NP has to be greater than or equal to 10. And NQ has to be greater than or equal to 10. So that's the first thing you want to check. NP is greater than or equal to 10. NQ is greater than or equal to 10. If this is true, then the binomial distribution, so call it R, can be approximated with a normal distribution that has mean mu equal to NP and standard deviation sigma equal to the square root of NPQ. Notice these are the same mean and standard deviation as our binomial distribution. So the mean and standard deviation of our normal distribution that can approximate our binomial distribution are going to be the same as the binomial distribution itself. Makes sense because, remember, mean and standard deviation measure where most of the data is, so our center, and then how that data spreads out away from the mean. So our standard deviation. So mean and spread should be about the same for both the binomial distribution and the normal distribution approximating it. So the only criteria that it has to meet, NP and NQ both have to be greater than or equal to 10. If either one of these fail, then you cannot do the normal approximation for the binomial distribution. So let's look at a couple of examples and see could we use the normal approximation or not. So decide whether or not we can use the normal distribution to approximate R the number of people who reply yes. And if we can, let's find the mean and standard deviation for that normal distribution. So 62% of adults in the U.S. have an HDTV in their homes. You randomly select 45 adults in the U.S. and ask them if they have an HDTV in their homes. So to be able to determine whether or not we can use it, so we need to define what N, P, and Q are. So remember, N is our number of trials. So in this case, we're randomly selecting 45 adults. So N is 45. P is the probability in this case that we're asking the number of people who reply yes for our random variable. So P is the chance they're going to say yes. So yes, in this case, they have an HDTV in their homes. We know 62% of adults have a HDTV. So probability of success, or probability someone is going to say yes, is 62% or 0.62, which then means probability of failure, Q, is 1 minus P. So Q is always going to be 1 minus P, so 1 minus 0.62. So we get a probability of failure in this case of 0.38. So now we just need to check what NP is. So N times P is 45 times 0.62. And so we get 27.9. That's greater than or equal to
10.
So we're good. So we move on to n times q. N times q is 45 times 0.38. And so we check that. We get 17.1, which is greater than or equal to
10.
So we're good also. So because both of these are greater than or equal to
10.
Yes, we can use the normal approximation. So because we can, now let's find the mean and standard deviation of this normal random variable. So remember, mu is going to equal the same thing so the mean is going to be the same thing as the mean was for our binomial random variable. So mu is equal to n times p. And we've already calculated that because that's one of our criteria to check to see if we can use the normal approximation. So n times p is 27.9. And then sigma is just square root of n times p times q. So square root of n times p we already know is 27.9. So 27.9 times 0.38. And when we work that out, we get approximately a standard deviation of 3.26 to two variables. All right, so go ahead and read through this example, pause the video, and try it on your own. All right, so same idea. We want to decide whether or not we can use the normal distribution to approximate our binomial random variable r, which is the number of people who reply yes, and if we can, find our mean and standard deviation. So 12% of adults in the U.S. who do not have an HDTV in their homes are planning to purchase one in the next 2 years. You randomly select 30 adults in the U.S. who do not have an HDTV, ask them if they are planning to purchase one in the next 2 years. So same thing, let's define what N, P, and Q are. So we know N in this case is going to be our 30 adults we're selecting. So our trials, our adults, are in this case 30. P, probability that they are planning to purchase one. So that's 12% or 0.12. Q then is 1 minus 0.12. Which then gives us 0.88. So same thing, we check N times P. So N times P is 30 times 0.12. And we get out 3.6. All right. So red flag, this is less than or equal, this is strictly less than
10.
And so because this is less than
10,
we're done. We cannot use the normal approximation. So in this case, if we wanted to find this probability, we would actually, whatever the probability is, we would have to actually use the binomial distribution and the binomial formulas. We cannot use the normal approximation for this problem. And so you would have to go back and use other techniques.